Okay, we're going to do a video for the next part of chemistry. It'll be specifically about electrolysis, but the course talks about metals and how we get metals. So just to start with, to sort of introduce that, we use metals in all sorts of places on Earth, but we can't dig up a metal mostly. There are a few metals, things like gold, that actually are in the ground as metallic gold. You can get a little bit of copper that way, but most metals that we use don't come out of the ground in their metallic form. They come out of the ground as an ore combined with other elements as minerals. So we need to do something to that to be able to convert it back to its metallic form. So normally we find them as ions, okay? And the important thing that we we probably know already is things like copper comes as 2+ ions, can come as 1+ as well. I know silver, positive ions, lead, what's another example? Zinc. They're all found in the ground, in nature, already in that ionic form, combined with other elements. Okay, so you get all sorts of ores that contain zinc or that contain lead, and that's what the miners mine. They mine out that ore. We then need to be able to convert it back into metallic form so we can use it as a metal. So all these things have a deficiency, or they don't have as many electrons as what they would have as their metal. They're 2 positive charge for copper, for example. It's lost 2 electrons to make its ionic bond, to make its ore. We want to get it to have those 2 electrons back again. That's our aim. So this whole topic is going to be about redox reactions. Okay, so oxidation reduction. Okay, we need to, in this case, we want to aim to get electrons back on. So a couple of things to remember about redox reactions. We have that sort of memory aid, whatever they call them, what we say oil rig, all right, and that is that oxidation is loss, reduction is gain. So OIL and RIG for that. What's really important when we're talking about that, it's always about the electrons. So it's the loss of electrons or the gain of electrons. It's not about charge. It's not about loss of charge, gain of charge. As such, it's about electrons. Now that changes charge, but think of it always in terms of electrons. So an example would be if I wanted to turn copper ions, so I've got copper 2+ ions, and I want to turn them back into just copper metal, then I'm going to need to put some electrons on it. So I need to add electrons. Now for every copper ion, I'm going to need 2 electrons to balance out that positive charge, the double positive charge for it. So that's what we call a half equation. It's called a half equation because that can't just happen by itself. It's not possible to happen by itself. We can't just pluck electrons from nowhere. Electrons don't just float around and we just put them in there. They have to come from somewhere. So we need another reaction to be happening at the same time where something is losing its electrons, losing those 2 electrons and passing them over to the copper. Okay. Now, if this is copper adding, or copper ions adding 2 electrons to it, then this must be the reduction half. This is the reduction half equation. Something must be oxidized, so there must be an oxidation half equation as well. Now that could be all sorts of things, and we're going to look at some examples in electrolysis how that works. So to get what we're going to be looking at is how can we, what processes can we use to be able to put electrons or force electrons back onto those ions to create our solid metals again. And it depends really heavily on a couple of things. Now, if I I'm going to skip down because I want to look at something, but we'll come back up in a sec. This is directly from your formula sheet, well, not your formula sheet, your periodic table. On the back of that, there is some information. This is part of the information, which is the metal activity series. And it's not all the metals, but you'll find that potentially this year's might have different metals on there, but it'll have the metals that are required for the exam that you're doing. What it's saying is that at the top with potassium, calcium, sodium, they are the most reactive metals. Most reactive means they react really well with lots of different things. We know that we put sodium, we can react sodium with water and, you know, catch some fire, it can explode. It is very reactive. Now that's sodium metal reacting with water and turning into sodium ions. So sodium metal would really like, you know, energetically like to be in its ionic form rather than its metallic form. So if we're trying to put the electrons back on to ionic sodium to get back sodium metal, you can probably imagine that if it puts out that much energy going from metal to iron, then you're going to have to put a fair bit of energy, a fair bit of effort to get those electrons back on again. So it's not an easy process. It's going to be very energy heavy, and other things will happen preferentially rather than that. As we go down that list, we get down to the bottom where we've got gold and silver and mercury. They are least reactive. They are much more happy to be in their metallic state. They don't tend to corrode. They don't tend to react with many things from their metallic state. Gold, silver will sit in the ground for millions and millions of years as just gold or silver and not react with anything, even under sort of the pressures and temperatures that you can sometimes get underground. Now, it doesn't mean they can't, but they tend not to. Why are they good for properties we use? We use them for jewellery because they tend to stay nice and shiny. They don't corrode. They don't react. You know, you can put them in piercings and that sort of thing, and it doesn't react with your body. So they're very unreactive. What that means is if we want to put electrons back on, if we did have silver ions, it's very easy, takes very little energy to put electrons back on and convert them back to the metal. That list is really important because often we'll be comparing two metals together and trying to work out what will happen. Now that's probably not in this topic as much, but we do need to be aware of it. And obviously the more reactive one is preferentially going to go into ionic form over the one that's less reactive, which is going to come out and be the metal. So why I want to highlight that is because to be able to create things like solid sodium metal, because it doesn't exist naturally on the Earth, it's way too reactive, it's all reacted, we have to follow different processes, and it depends on how difficult or how reactive the metal is to what process we might use. Okay, so I'm just going to go back up to here. So one of the processes that we're going to use are electrolysis. Okay, and this is actually what we're going to do our prac on. So that's why I'm sort of trying to get some information about it. What's really important is that later in this course we're going to meet what we call galvanic cells, which look similar, and it's still reduction, oxidation, but there is a difference that's really important. What we're doing here is trying to force a reaction to occur that won't sort of happen naturally. The way we're going to force that is to put electrical current, or put a potential difference, use electricity, use the energy of electricity to cause a chemical reaction to occur. Okay. The other ones we'll meet a bit later. They are sort of the opposite. They are your batteries. They're where we're using a chemical reaction to create electricity. For this, we are using electrical energy that we will get from, we can do it in our lab. We'll get it from plugging into a power point. We'll use that electrical energy, but in other situations, they'll get a lot more energy from other sources in industry. But we're using that to make a reaction occur. So that's what we're going to be working on. One other thing to remember, and I'm sure I've said it before, but we're going to be dealing with the cations and anions. Remember, they are cations, they're not cations. It looks like cation, but it's a cation. One of those is a positive, one is negative. You might just remember it, but if you can't remember it, you can think of the cations, pus for cat, so positive. That will, that's a way to remember what they are. Then the anions are the negative ions. Okay, ideally you'll use that language more when you're answering questions, when you're writing about things, rather than saying the negative ions, the positive ions. You would say the anions, the cations. Okay, so try and get used to that language with it. Okay, so the first thing that comes from the curriculum statement. This is not the order of the curriculum statement, this is the order from the book, but it works well for us getting ready for the prac. Is to look at these electrolytic cells. So this is one way we're going to do this, force this reduction to occur so we can create metals, okay? It's not the only way, and we're going to talk about other ways in subsequent lessons, but we're going to focus on these for the minute. So the first thing that we are going to look at is the diagram. It says we're going to identify an anode and a cathode, their charges, the direction of ion flow, all this sorts of stuff. And there is a table, I didn't copy it in, there's a table in the SASTA book, there might be one in the other one as well, that talks about all those things, so you can have a look at that yourself. But we also need to be able to write these half equations, okay? Now this is an electrolytic cell, it means that the reactions are occurring, so you must have both half equations occurring in this space. You must have the reduction and the oxidation occur. So if we have a look at this, this diagram, you want to get used to what they look like. We've got a few things on there that are important. We've got this symbol that's used to represent a power supply. It's saying we are providing power to it. We aren't taking power away from it. We're providing power to it, okay? And we are providing, what's really important is we're providing, it doesn't say that on here, but we're providing a direct current. So it'll always be DC. So when we do our prac and we're plugging into the power supplies, we cannot do this on the AC terminals because that tells us we have an alternating current, which means it changes these two from being positive and negative. They will continually flip backwards and forwards. What happens is then your chemical reactions are swapping your two electrodes are swapping their sign lots of times a second. We don't want that. We want the signs of those electrons to stay the same, electrodes to stay the same. So we're providing a direct current. And in this diagram, what we're doing is we're forcing electron flow into this way. I should draw that so it stays on. So let's just get another color. All right, we're forcing electrons. All right, we're pumping, if you like, we're pumping electrons to this point here, and they're going to try and get away from each other, so they're going to head down that electrode. Okay, so we have the electron flow going down that electrode. Okay, so what that means is we're going to have excess electrons sitting in here. A bit hard to see, possibly. I might just be able to see them. There's extra electrons there. Now, they don't want to be there, really, but we have this push from the power supply pushing them down there. So really the only places that they can go are out into the air, which they're not going to do, or they're going to have some sort of reaction happening at the surface of that electrode that's touching this liquid, this electrolyte that it's in. Okay, now it's an electrolyte. Electrolyte just means that it is a solution that contains ions in it. Okay, so it could be a solution, which means it's dissolved in water. It could be a molten thing. We'll see them in a minute. So what's going to happen if we've got a whole heap of extra negative charge on that electrode, then any positive ions, like this one's been labelled as C+, are going to be attracted to it. Okay, positives and negatives attract, and they're actually going to move. That red arrow there tells you they're going to move towards that electrode. And when they come in contact with that electrode, electrons, the excess electrons, can jump over, and sort of the C plus, this ion, can actually gain that electron. Now it's gaining an electron, which means it's being reduced. Reduction is gain. Okay, so that occurs at that interface between the electrode and that surface. Now, as soon as that becomes just a C in this case, it's no longer attracted to the electrode anymore. It's not charged, so it doesn't have that attraction, and it'll just wander off. Now, it depends what it is. Is it a metal? It might actually get deposited onto that. It might not wander off. It might get sort of stuck onto that electrode. In some cases, it can cause a gas to form, and if it's a gas to form, it'll bubble off. Okay, there's lots of different things that can happen, but something will happen to it. But then more of these C pluses will come, and this process will continue. Okay, now what that does, okay, is a couple of things. One of them is that it would potentially change the charge that's in this electrolyte, because we're losing positive charges, which would make the electrolyte become, over time, more negative. That's not favourable. That doesn't happen. It can't have an electrolyte that has a whole heap of extra negative charges than positive charges. Okay, something else is going to happen. So the negative charges are going to tend to want to go this way. Okay, and the electrons are being sort of moved along here. They're actually moving up. I'll draw there, up this way. So that electrode being positively charged, because electrons are leaving that space, that will accept extra electrons if it can. All right, and if we have a look, we've got this ion here, whatever A is, it's negatively charged. That can move over there, and it can actually give up an electron. Okay, so it can give that electron up, or 2 electrons, depending on what it is, and it can be then changed back into another form. Now, if it's giving up an electron, then it's oxidation. Oxidation is lost. It's lost an electron. Okay, so that occurs there. All of that continues to happen. What it does, it keeps everything in balance. It means the electrolyte is always going to be neutrally charged overall. Okay, as these C's lose their positive charge, A's are losing their negative charge. Okay, and that process will continue. That's the basic process, but some of the things we need to be really aware of. We've got the negative electrode being called the cathode, the positive electrode being called the anode. Now, I don't want you to remember it like that. I don't want you to think negative is cathode, positive is anode. Okay, and you're going to say, why not? Because all of the ones that are electrolytic, that's what's going to happen. You'll see a bit later why not. What I want you to remember is that the reduction, so where reduction occurs, is at the cathode. And oxidation is at the anode. Okay, that's really important. So, what I want you to do is to remember that. The best way to remember that is to just think of this. Okay, red cat. And you can even think of an ox, if you like, as well. So the animal sort of thing, but certainly red cat is a good way of remembering it. Red cat, okay, reduction, cathode. Anox, anode, oxidation. That's just a common way to remember them. It is important that you do remember which happens, because it could be that you have to say, well, you know, you give them a diagram, which one's the anode, which one's the cathode. Okay? So use that as a way to remember. Okay, so that's the basic process of it. Just a couple of quick examples. I don't want to go too long because we've gone a bit long as it is. But there are going to be different situations that we need to deal with. So we talked earlier about the fact that sodium really doesn't want to be its metal. It's quite reactive. It would prefer to stay as a ion. This is another example of something, so like bromine, which wasn't on your list, but it's quite reactive. So if we were to do this electrolysis in an aqueous solution, meaning that we had some of the lead bromide, we dissolved it into water, what we'd find is, in fact, perhaps some of the water itself would be part of either the oxidation or the reduction, because it's less reactive. It's more happy to be changed. It's more happy to be reduced than what the bromine is. So we can't do it in water. What we actually would have to do to be able to do this process would be to actually make that lead bromide molten, so that the only things that are in that, the only things that are in here are just bromide ions and lead ions, because we've melted it. We haven't dissolved it in water. Okay, so we can do electrolysis molten. So in this case, notice that they've used graphite as their electrodes. Graphite, one, because it's very unreactive, it's just carbon, but it also melts at a very high temperature. So it can be placed into molten solutions and not melt, but still conduct electricity. Okay, so that's really important. What we've got is, let's just get another colour. We've got the same situation. The electrons are going to go down this way. You can see where the negative side is. All right, so the lead, okay, and I think I was talking about bromine, but it's lead that we're interested in here. The lead is going to come from its ionic form. It's going to grab the electrons and become lead metal. So we would have lead 2+, okay, plus, and we can actually write liquid in this case because it's actually molten. And we're going to get 2 electrons, and we're going to head to lead metal. And it's probably not actually going to be solid because it's the temperature. It's probably also going to be liquid when it forms. Okay. Now, in this process, what it might do is make a liquid that might be more dense than the liquid of the lead bromide. So it might sink, and you could tap it off the bottom. It's probably going to be more dense, I would suggest, and that's what you would do. But you know, something's going to happen with it. Now, if that's happening, remember this is reduction. Okay, reduction is the gain of electrons. So we have added 2 electrons to our initial starting point. Then we must have an oxidation one. You can see that on the diagram we've got bromine ions. So we've got bromide ions there. They would be also liquid. Okay, and what they're going to do is deposit their electrons over onto that graphite anode. Okay, so they're not going to, let's make that bromine, and now it's probably liquid, it's 2, okay, so we actually need 2 of those, and there are 2 electrons here, okay, so the electrons on the other side, the bromide ions have lost electrons, so it's oxidation. So we see oxidation occurring. Okay, so that's part of the information that you would need to be able to deal with. You need to be able to write those little half equations. Okay, now the overall equation, because we have 2 electrons on either side, the electrons sort of are taken out of the overall equation and so we get anything that's on the left-hand sides. So we're going to have lead 2+ plus 2 bromides goes to lead plus Br2. That's the overall, okay, overall equation. So that's stuff that we can get from it. If I zip down a bit further, quite often we could do aqueous electrolysis, which means that we can dissolve it in water. So we can with lead if it's lead sulfate that we're dealing with. Okay, so lead will be reduced okay, in preference to water being reduced. But in this process up here, what would happen is that we wouldn't be able to deal with the bromide ions. Okay, they wouldn't be oxidized. In this case, the water would be oxidized and we'd cause some problems. Okay, so in this one, the reactivity of lead is okay. It's going to be reduced instead of water. And in fact, in this case, it doesn't actually matter that water is being oxidized. Okay, so we can deal with those as aqueous. We would need to be told what's happening with, is it water or is it the sulfate ions? Because in this solution, there are also going to be sulfate ions floating around as well. So what we don't know without sort of being given some information is that these could potentially go there. They'd be attracted to it, okay? But in fact, water itself, okay, can be split, and we'll do that preferentially over the sulfate ions. All right, now, you don't have to know that information. That sort of information will be given to you, okay, in a question. So that is why we have to be a little bit careful with aqueous ones. So you could imagine that if I had an aqueous solution of just sodium chloride, so just salt water, and we did it, what is unlikely to happen is that the sodium ions become sodium metal, because that's a very difficult process to occur. And so it doesn't. Right? So the sodium ions are not going to be converted into sodium metal. Water, in fact, in that spot will be reduced instead, okay, because it's easier to reduce water than it is to reduce sodium ions. So we have to pick what we're going to do depending on what we want as our products. So just as a last one, the electrolysis of water. So if we just put water in, then what's important is that we look at what can possibly happen if we put some a very unreactive salt into it. Because water itself, pure water, doesn't conduct electricity. It doesn't have enough ions in it. Remember that water, pure water, the pH of 7 means that it has 10 to the minus 7 H pluses and OH minuses. So it doesn't have very many ions at all. It really doesn't conduct electricity. Why is electricity dangerous with water? Because we don't have pure water very often. If we're in the bath, there's soaps and there's oils off your body, so there's lots of ions in there. You drop your hairdryer in, bad news. In a pool, there's chlorine, there's all sorts of other ions in there, so it'll conduct electricity. Pure water doesn't conduct, so we can't really electrolyse pure water. What we can do is put in some ions that aren't going to be oxidised or reduced in preference to water. Water will still be done. So just to write those down, we can have water, okay, and we could add electrons. So if we're adding, all right, reduction is gain. So this is reduction, okay. What happens is we end up with hydrogen gas, okay, and hydroxide ions. So these would be aqueous. We're going to need 2 of those. So what do we need? 2 of those as well. 2 of those. Okay, so that is reduction. That's the reduction of water. So you can see that water itself isn't a charged molecule, but it still contains electrons. We can actually cause a chemical reaction. That what happens is we actually change the oxidation state, and we seem to be not worrying about that too much in this course. We used to do a lot more work on that, but we're changing the oxidation state of the hydrogen from what it is in water to what it is in hydrogen gas. So that's the reduction of water, but we can also deal with water and say it can also be oxidized, which means that it must drop some electrons, okay, and it can be converted to oxygen gas, hydrogen ions, and then there's your electrons. Okay, so this is oxidation. So water can be oxidized and it can be reduced. Okay, products are going to be different. We can see that we get in reduction, we're adding electrons to the water. Okay, in oxidation, we've taken away. We've had water and we've split it up into these things here. So we've taken the electrons away. Okay, so quite important that you see that that can occur. That has a ramification for whether or not you can do aqueous electrolysis. Why would we want to know that? Well, we'd want to know it because if we were industrially trying to create a metal, reduce a metal from its ions, we want to do it as cheaply as possible. And you can imagine the energy required to keep this solution here molten is going to be huge. We've got to have a really high temperature and we're pumping electricity there, not to mention the fact that we're pumping electricity here. So that's an expensive way to do it, but if we've got no other choice, that's what we'll do. But if we do have a choice of doing aqueous electrolysis, then this can be just left at room temperature. We don't have to heat it at all, and we save a lot of energy cost. So we need to know about what's happening with that. Okay, so that should hopefully give you a bit of a start on some of this stuff. The questions 151, 152, and 153, they can be done from the SASTA book. There's probably some other ones in the Essentials book, but they may not be in the same order. We're sort of just following through that SASTA one. Okay, good luck.